Hello everyone, my name is Randall from Technocamps. Thank you for watching this video. Hopefully, by the end of this pack, you will have a sound knowledge of what binary is, be able to count using 4 bits binary and maybe more, have a good understanding of other different number systems, be able to use the Technocamps AR binary app, and be able to complete the quiz at the end to win some prizes. Um, There will be a second video where we will showcase the app, and in that video you will learn how to use the app and where to sort of download it, how to install it, and where to get the QR codes that you need to use the app. Now, before we look at what binary is, we first need to understand how number systems work. There are a huge number of number systems that you may not have heard of. However, you should know the decimal number system. The decimal number system is the number system that you use in your daily life. It consists of these digits displayed, and you use them for mathematical calculations. Now, before I move on, I want you to have a think of why 10 or 10 is not included in the list. The decimal number system has another name for it. It can also be called as base 10. As I've stated, there's a number system that we use every day. It consists of 10 digits starting at 0 and ending at 9. Using this decimal number system, we count like this. We start with 0, then we add 1, then we add 2, and so on. We go up to, let's say, 9. So here we've got 9 black dots, okay? But after we add 1 to the 9th digit, what we actually do is we start back at 0, but add 1 to the left. Now this value for us is commonly known as the number 10. But actually, what we've done is we've started back at 0 and added 1 to the left, restarting the sequence. And if we keep going, this is how we would continue to count. So we change that 0 to 1, then we keep going, keep going, keep going, and again we follow the same process. We reset the value on the right side to 0, and we add 1 to the digit on the left. And again, if we keep going, okay, we keep adding 1 to the right. Once we hit the 9th digit, we reset that digit to 0, but add 1 to the left. When we count, we use symbols. In number systems, we often use digits over and over again. However, the location of those digits changes their value. So in decimal number systems, or base 10, we have these following units. So units are 1 to 9, then you have your tens, then you have your hundreds, and then you have your thousands. So depending on where those digits are located, it changes their values. So if it's all the way to the right, there are units. If it goes more towards the left, then their value increases. So as you can see here, we've got £1, £10, £100, and £1,000. The more far left the digit is, the more it's worth. In decimal number systems, we use units, tens, hundreds, thousands, and so on. Mathematically, they are represented as 10 to the power of 0, so units, 10 to the power of 1, tens, 10 to the power of 2, hundreds, 10 to the power of 3, thousands, etc. Now, so I've used a table to represent exactly what I mean. Any number to the power of 0 will always be 1. Then 10 to the power of 1, if you type that in your calculator, will give you 10. 10 to the power of 2 will give you 100. 10 to the power of 3 will give you 1,000. So in math, the way we represent sort of each unit, it can be done in this sort of expression, 10 to the power ... So if I wanted to expand my my table so that I can represent 10 thousands, and then that would be 10 to the power of 4. Now, I've mentioned before that um, when we count, we often use symbols, and we just repeat those symbols over and over again. Now, the Roman numeral system is a good example of this. Even though they don't use the digits 0 to 9, they use other symbols which represents those values. So if you don't know your Roman numerals, this is what it looks like. 1 is represented by this sort of line. 2 is 2 lines together. 3 lines together. But then 4, you replace the 2 previous lines with a V. So it's now IV. 5 is V, and 6 V, but this time the line's sort of on the right side, so on, so on. So as you can see, there is sort of a pattern. In the beginning, the lines are on the left side. Then when it hits any number before and after multiples of 5s. So as you can see here, any number before and after multiples of 5, the symbols will be changed, but then the lines, if it's before 5, the lines will be on the left. If it's after any multiples of 5, the lines will be on the right. And the actual value or number that is a multiple of 5 will be the new symbol or symbols on its own. So if we take the value 10, which is a multiple of 5, as you can see, the number before 10, the line is before the new symbol, which is X. 10 is just X on its own, whereas 11, this time the line is on the right side. So as we can see, there is a pattern with the Roman numeral system, and it's the same with the number system that we'll be looking at today, in particular binary numbers. So currently, we've talked about one number system, that is the decimal number system, or base 10. Even though the Roman numeral system uses different symbols, they still operate the same way as the decimal number system. That is to say, they use 10 digits, 0 to 9. But there are other bases. One particular base that is the main focus of this video is is binary, or also known as base 2. And in the binary number system, we only use 2 digits. They are 0 and 1. And if we were to count in binary, we would count like this. We start at 0, then we add 1. When we add 1 again, we reset the value on the right, and we add 1 to the left. So even though we know this as in decimals, commonly as 10, in binary it's actually 1, 0. We do the same thing. We continue to add. So we change the 0 to 1, but because again there's only 2 digits in binary, we've reached the end of our sequence. Therefore, what we need to do now is move on, change the right hand side value to 0. Also, because remember we're only using 2 digits, after 1 we have to change this one to 0 as well, and then add 1 to the left. So the equivalence of this in decimals would be, let's say we had 99. So if this was 99, when we add 1 to 99, the first 9, the one on the right, will be turned to 0. Then we add 1 to the value on the left, which is also 9. So that again is changed to 0, and then that 1 goes towards the left, giving us 100. So it's the same thing, so sort of same principle that's being used there. So again, we start back at 0, we add 1 to the number on the left, but the number that's already at 1, so it also goes back to 0, and 1 is added to the next position on the left. Now, in binary, instead of using units, tens, hundreds, and thousands, remember, mathematically, those are represented as 10 to the power 0, 10 to the power 1, 10 to the power 2, and 10 to the power 3, etc. In binary, we use the following mathematical expression: 2 to the power of 0, 2 to the power 1, 2 to the power of 2, 2 to the power 3, etc. So this is what would look like if it was a table. Okay, so instead of using units, units, tens, hundreds, and thousands, this time we use these. Remember, a number to the power of 0 will always be 1. So even though it's 2 to the power 0, it'll be 1. You'll just have to take my word for that. It's how it is in math. Instead of using 10 to the power 1, this time we're using 2 to the power 1. Again, if you type that in a calculator, that will give you 2. 2 to the power of 2 will give you 4. 2 to the power of 3 will give you 8. So this time, instead of adding up, let's say in decimals, you add up the tens, the hundreds, the units, the tens, hundreds, and thousands to get the final value. In binary, we add 1, 2, 4, and 8. So here's an example. If we have a 1 on the rightmost, that will give us a value of 1. If we have 1, 0, that will give us 2, and then so on. 1, 0, 0, 0 will give us, there's an error there, that should not be 6, that should be 8. So it's sort of like a light bulb sequence with binary. It's either on or off. So if you see 0, that means this value 1 is off, so that value is not added, but this value 2 is on. So you add the total sort of scoring, so in the end you get 2. In binary, you often will have the zeros on the left side. So even though you can write them as 1, 1, 0, 1, 0, 0. Sometimes they are written as 0, 0, 0, 1 for the same value, or 0, 0, 1, 0 for 2. It's the same with decimals. In decimals, you look at the value, let's say 100, but actually that 100 could also be 0, 0, 0, 0, 100, but it still has a value of 100. These are just written with binary more than it is with decimals. So yeah, given that fact, binary can be represented in various ways. So 4 bits binary, where we have 4 digits are used, is represented in this way. So 001 is actually 1, 010 is 2, 0011 is 3. Again, the way we work that out is if I go back here. Okay, if we think about it as light bulbs, this is on, all the rest are off. So instead of adding all of these up, we only add the 1, giving us 1 as a final value. Same thing here, off, off, on, off. So 2 is on, meaning the final result will be 2. If I do another one here, again, this should be 8, not 6. 1, 0, 0, 0. 8 is on, meaning we have the value of 8. All the rest are off, meaning we're left with a value of 8. Okay, so that's 4 bits binary, but you can extend that to 8 bits. So as you can see, in 8 bits, to represent the value 1, you need 0, 0, 0, 0, 0, 0, 0, 1. It's just saying we've got 8 different bits, or 8 digits that will represent that 1 value. As you can see, they're still equivalent. The value is still the same, but you have more digits to represent that value. So the reason for these representations is here we're showing the fact that in 8 bits, we can essentially count up to a higher value. Whereas with 4 bits, we have a smaller amount of numbers to count up to. I will explain that a bit more in the following slides. So let's take an example. So like I said, 2 to the power of 0 will always be 1, 2 to the power of 1 will be 2, 2 to the power of 2 will be 4, and 2 to the power of 3 will be 8. So in binary, 0, 0, 0, 1 will obviously be, ooh, something's wrong there, will obviously be the value 1. So as you can see, off, 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 on, so we have 1. Obviously 0, 0, 0, 0 will be the value 0. If we look at another example, this time we got 0, 1, 0, 1. Again, remember 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8. So here we're saying we're adding the value 4 and the value 1 together. And if I display it in light bulbs, off, on, off, on, have a think what this value is, or what it is in decimals. So this is what the value is in binary, but in decimals it is, so I'll pause here for a few seconds for you to work it out. Right, so hopefully you were able to figure out that the value of this binary representation in decimal is 5. So again, that represents 4. So we're adding 4. This represents 1 to 1, giving us 5. Here's another example. Okay, 1, 1, 0, 1. If it helps you imagining it as light bulbs, here it is. Again, I'll pause for you to work it out. Right, okay, so hopefully you were able to work out that 2 to the power 3 is 8. So we're adding 8 to 2 to the power 2, which is 4, giving us 12. This is off, so we don't add that, but this is on, so we're adding 1 to our 12. So this is 13. So that's the binary representation of the number 13. Last one. Okay, so that's what it looks like as the light bulbs. Right, okay, so hopefully again you had enough time to work it out. Again, so here we're adding 8, 4, 2, and 1 together, giving us 15. And actually, in 4 bits binary, 111 is the max number or the upper limit of 4 bits binary. So in 4 bits binary, we only count up from 0 to 15. Now, knowing that, what I want you to do as homework, I guess, is figure out how many numbers there are in 8 bits binary. And now we've only talked about 2 different number systems, base 10, so that's the decimal number systems that we use every day, and base 2, which is the binary number system that computers use to do things, okay? There are various other number systems, such as ternary, base 3, quaternary, base 4, and quinary, base 5, and so on. If you want to find out more, go to this website. Okay, I'll pause if you want to copy down, go to this website. But if I go to it myself, I already had the app. This is a website, it just shows you base 10, so this is how we count. Base 2, this is how we count in binary, and it shows you other number systems, so base 3, 4, all the way up to base 20. Okay, now hexadecimal is another interesting number systems that are used heavily in computer science. Okay, and if I just go back to my slide, starting from base 11, I think it's base 11, yeah, starting from base 11, not all number systems are represented using the digits 0 to 9. Some number systems use letters in addition to those 0 to 9 digits. Base 11, and in particular hexadecimal, or base 16, is one of those. So here's the table. As you can see, when we get to 10, or in hexadecimal 10, we start using letters. So we have A to represent 10, B for 11, C for 12, etc. Now base 16, now I'll only talk about this briefly. What you can do if you are interested is look this up more for yourself. But if I briefly talk about base 16, so in base 16 we use 16 symbols. So 0 to 9 is 10 of them, but the other 6, 10, 11, 12, 13, 14, 15 are in letters A, B, C, D, E, F. Now, once we get to the 16th, 16th digit, we perform the same thing. We reset, so we change that to 0, and then we add 1 to the left. But with these number systems, it gets complicated. So if you look at the bottom here, okay, you have 25 in decimals, but in hexadecimals is actually 19. But then as you keep going on, you get to 1A, 1B, 1C, 1D, 1E, 1F, etc. Now this can take a bit of time to get used to, but the same principles are still in play. You have your 16 digits, 0 to F. And then once you reach F, you reset to 0 and add 1 to the left. Okay. Yeah, give that a go. You don't have to understand this for the quiz, but I thought it was something that you, again, something that you can look at if you're interested. Okay. Right, so I'll leave it there. Thanks for listening. Hopefully, this makes our number systems and binary more makes them more sense, and maybe you have more of an understanding of them. Look out for video number 2, where we will be given a tutorial on the Technicams AR binary app for you to use.